So today we're going to be talking about maps from the plane to the plane. What's this? Wait, what the heck are maps? Maps are also called transformations. That's another word. And both of those words, they just mean functions. But we're often going to call them maps or transformations in this context. They take a point in the plane. They spit out another point in the plane. So these are not scalar valued functions. These are vector valued functions. Let's start off by, let's start with some set in the plane. Let's D star be some set in the plane, and our map or transformation, I'll use the letter T for, it's a map from D star back into the plane. And we're going to suppose that T is, okay, here's one that I know you guys will like. Continuously differentiable. Oh, what does that mean? Yeah, what's continuously differentiable? It is different. So yes, it includes differentiable. It's stronger than differentiable. So differentiable means that, well, it has a derivative. The derivative exists. You can, in this case, it would be all of its partial derivatives. But the continuously part means that, moreover, all those derivatives are continuous. All the first partial derivatives exist and are continuous. For more on that, I refer you to section 2.3 of the textbook. But there's a word for continuously differentiable which we will sometimes use. It's sometimes called C1. So aka C1. The 1 means its first derivatives exist, and the C means continuous. First derivatives are continuous. So you can see, this book talks about C1 and 2.3. Let D in R2 be the image of T, i.e., okay, so what does that mean to be the image? D is all the points in the plane that are hit by the function that it sends values to. So D is the set of all xy such that xy is the image of some point under the transformation T. Okay. Stop me if you have a question on this. You could also write D as simply the set of T of, let's say, x star, y star, for x star, y star, and D star. Or, here's a pretty nice shorthand notation for this. It's simply, it's T of all the points that are in D star. So I like that. That's a nice short way to write it. So that's the image of T. Let me remind you of what it means to say that two vectors are equal. So recall that if we have two vectors, let's say AB and CD are equal, in which case we write that AB is equal to CD. If, what does that mean? That single equation actually stands for two equations. It stands for A must equal C and B must equal D. Right? So saying two vectors are equal means each of the components are equal to the corresponding component in the other vector. Here's an image. So let's say here's the xy plane, and how about this is D star, and it's going to get mapped via the transformation T to some other set, also in the plane, which is D. For example, how about if D star is 0, 1 cross 0, 2 pi. So this is a rectangle, but the transformation T will be given as follows. So you know how a gentleman over here had a question. Sorry, what was your name again? Joseph asked a question about labeling of variables. And I said they're usually x and y, but not always. So now I'm going to call them r and theta. And we're going to see a few other examples of them in the next few lectures where we use various different names other than x and y. The point is the variable that you list first corresponds with the interval you list first, and variable you list second corresponds with the interval you list second. So t, I'm going to use r and theta for the variables that t is acting upon, which you'll see the reason for. T of r and theta is equal to r cos theta, r sine theta. So what is T of D star in this case? Well, you might recognize the form of T, but let me do a brief aside. Let me review polar coordinates for a moment. So these polar coordinates are going to keep coming back. If you're going to need to have a firm grasp on polar coordinates before you can even start to mess with cylindrical and spherical coordinates. So let's do polar coordinates first. So the polar coordinates, which I think you probably learned maybe in pre-calculus, is where you take a point in the xy plane. So let's say this is the point xy. Then you can draw a triangle where this side is of length y and this side is of length x, which means that the hypotenuse is of length x squared plus y squared under a square root sign. And we're going to call that r. by convention, we always label the polar angle counterclockwise with respect to the positive x-axis. There's nothing special about that. It's just like it's easier if we all agree to do it the same way. So we're always going to measure theta right here. And then you can see from this triangle that y is equal to r cos theta and x is equal to r sine theta. So that's how you could convert from the polar coordinates to the rectangular coordinates. You could convert from rectangular coordinates to polar coordinates using this formula for r. And the formula for theta is a little bit trickier. Like in the first quadrant, for example, you have the relationship that theta is tan inverse of y over x. Let me just do a quick little example to show why that formula doesn't always hold. So let's, oh, yeah. Oh, thank you. Cool, yeah, all right. Y right here is r sine theta, and x down here is r cos theta. Thank you. Let's find the polar coordinates of the point. How about -1, -1? So that's this point right here. R is pretty easy. It's the distance from the origin, so that's the square root of -1 squared plus -1 squared, which is root 2. What's theta, though? I caution you against using tan inverse, because some students, they just punch in a formula and they don't even think about whether the answer makes sense. It bugs me. I'm like, did you draw that? Like, does that even put you in the right freaking half of the universe where your answer is? So please draw a picture when you're evaluating these angles. And if you draw a picture, you can see that, okay, we've got to go around, what is that, 225 degrees to get to theta. What is that? It's 5 pi over 4. Okay, so that's your theta right there. And there's different formulas. I usually just like drawing a picture, really the easiest, and then using reference angles. But I refer you to examples in the book for more practice with that. Anyway, so that's my polar coordinates review. Now let's go back to what I was talking about, which was this transformation T, this one. So we see that, hey, this transformation, that's exactly just the polar coordinate formula. So T of r theta equals r cos theta, r sine theta. If some point x, y in the range of T is equal to T of r and theta, i.e. x is r cos theta and y is r sine theta, then r and theta are exactly the polar coordinates that I just reviewed for you. So to figure out the range of this transformation, let's look at the domain. The domain was this set right here. So let me draw that set. R went from 0 to 1. Theta went from 0 to 2 pi. So under the image of the transformation, we're going to get all the points whose radius is from 0 to 1 and whose polar angle is from 0 to 2 pi. What shape is that? Unit disk, yeah. So it includes, yeah, everything from radius up to and including 1, but also less than 1. And the 0 to 2 pi means it goes in a whole circle all the way around 360 degrees. It's exactly the unit disk, right? So T of d star equals d equals the unit disk, which we've already seen. Note, wait, hold on a second, sorry. Okay. Actually, yeah. That's it for that example for now. Now, a particularly important type of transformation that we're going to study, ubiquitous form. Hey, Math 18 was a prereq for this class, right? No? Yes? Is it? Linear algebra? Is there anyone in here who has not taken linear algebra? Oh, good. All right. Whew. Okay. Good. All right. So from linear algebra, you might recall we talked about linear transformations in linear algebra. And they play a particularly important role in calculus. Those of you that have me for linear algebra, I said to you that you look closely enough at every differentiable transformation, and it looks like a linear transformation. So that's why study of linear transformations is sort of crucial importance for the study of continuously differentiable transformations in general. Here's a fact about linear transformations. Every linear transformation on the plane is of the form matrix multiplication. In other words, it's of the form T of xy, it's equal to, say, ax plus by and cx plus dy, which, if you will allow me to write this in matrix notation, you could also write as the matrix A, B, C, D acting on the vector x, y. Yeah. Here's another fact about linear transformations. Or maps, either or. Linear maps from R2 to R2 with non-zero determinant. In other words, what's non-zero determinant equivalent to? I knew Alex knew this. Yeah. It's not. In other words, it's invertible. If they have non-zero determinant, they take parallelograms to parallelograms. So like, for example, something like, oops, this would get mapped under the transformation to some other parallelogram. Maybe here. So like, let's say if this was one side and this was the other, then maybe it would get mapped to something like this. Where, for example, let's say this is the point x, y. If that's that vector, then this would be the point t of x, y. So you'll use that property on one of your homework problems, which I haven't actually posted yet on Canvas, but I will shortly, like right after this class. So you'll use this on 6.1 number 3, for example. Okay, now I'm about to talk about something which I know you guys will like, one-to-one and onto. Okay, yeah, I got a lot of grumblings about that back in linear algebra and when I did this before. So let me give you some perspective on it. Before we talk about maps from the plane to the plane being one-to-one and onto, you know, I think one of the reasons why it's tricky is because some students just try to memorize the definition. But how about you understand the concept? So let me review one-dimensional functional concepts first. So here's a one-dimensional review first. For g being a function, let's say g is a function of one variable. Okay, so then we say that g is one-to-one if, what does that mean? It means if g of x equals g of y, well then x must be the same as y. It can't be taking two different points to the same value. So here's some pictures. How about if we considered g from R to R given by g of x equals x cubed? So that looks like this. Is it one-to-one? Is x cubed one-to-one? It is, indeed. Yes, so this is one-to-one. Okay. What about g from R to R, g of x equals x squared? Like this. Is this one-to-one? No, it's not. So, because you can see, for example, these two x values both yield the same y value. Can't be having two different x values output the same y value. On the other hand, check this out. This is something which we may occasionally have to do. Consider g just defined on non-negatives. G of x equals x squared. So it looks like the same function as the previous example. Is it the same function? The definition of a function includes its domain. The domain of a function is part of the definition of a function. Does it have the same domain? No. So it's not the same function. This is a different function. Is this one one-to-one? This one is one-to-one. Okay, so that's something you might occasionally have to do. You can take a function that's not one-to-one, but if you properly restrict its domain, you can make it one-to-one. How about for onto is the other thing we're going to talk about in 2D, but first I'll again review the one-dimensional. So we say that G from, let's say, D star to D, and these are two sets in R, okay, is onto means, what does that mean? That means that for all points y in the codomain, there exists an x in D star such that g of x is equal to y. It hits every point in the target set. Finally, and this is something we're not going to do today, but we will soon, G from D star to D is invertible if and only if it's one-to-one and onto. Well, here, let me write the definition, sorry. It's invertible if there exists some function G inverse, which goes from D to D star, such that G inverse of G of x is equal to x for all x in D star, and G of G inverse is x for all x in D. And then the reason, like, we talk about all these concepts together is that a function is invertible if and only if it is one-to-one and onto. Cool. Okay, so that's my little 1D review. Back to 2 dimensions. So I'm going to do like the 2-dimensional counterparts of the definitions that I was just giving you. So let's let D and D star now be subsets of the plane. And T, some map from D star to D, be C1. Remember, that means continuously differentiable. That's what the C1 means. We say T is 1-to-1, and we'll often just write 1-1 if. Okay. See if I can write this definition. If T of xy equals T of x prime y prime implies that the point was the same, meaning the two coordinates were each the same. X was equal to x prime and y was equal to y prime. So you can't be sending two different points to the same point. We say T is onto if for all xy in the target space, there exists a point, at least one point, x star y star in the domain such that t of x star y star is equal to xy. All right, so every single point gets hit. Let's see an example. How about if t goes from R2 to R2 and is given by t of x, y equals x squared y? Let's discuss whether it's onto or one-to-one. What do you guys think? Is this one onto? It needs to be able to hit every single point in the plane in its range, right? But the first component, like the x component of the output, it's always positive or non-negative, right? This part right here is always greater than 0. So how are you ever going to reach the points with negative x value, right? Like whatever, well, the domain, sorry, the domain's the whole plane, but whatever the range looks like, I'll tell you what it doesn't look like. It does not include any points in the left half plane, for sure, because, well, the first coordinate is positive. Okay, so cannot be onto. And in fact, FYI, you can show that the range is actually exactly the right half plane. But the point is, it's not onto. So what about one-to-one? You guys think it's one-to-one? Well, so it can't be taking in two different points and outputting the same point. Like, how about the point 2, 7 and the point negative 2, 7? 2, 7 gets mapped under t. Here, sorry, let me write this a little bit different. T of 2, 7 is 4, 7. T of negative 2, 7 is also 4, 7. So I just took two different points but mapped them to the same point. So it's not one-to-one. Yeah, so we can't invert that one as defined. Mm-hmm. Yep. Mm-hmm. Alex? What does C1 sign? C1 means continuously differentiable. The 1 means you're talking about the first derivative. The C stands for the word continuous. So it's like the first derivative is continuous. Yeah?
So one-to-one essentially means that every mapping that we do has to be unique?
Yeah, it means like function values are unique. You can't be having multiple points going to the same point. You should read the textbook. So the textbook has a few examples of this, which will probably be helpful. Like, for example, example 3 in this section of the textbook has some useful stuff in it about limiting your domain so that your function becomes one-to-one. right? Because what's the problem? So the most look, we're learning all this in order to apply the next section in the textbook, which is 6.2 on the change of variables. Before you can apply that, you kind of have to understand when you can apply it. And what's the case which we are most interested in applying it to is polar coordinates, cylindrical coordinates, and spherical coordinates. So those are the examples we're going to focus on the most. There's a problem with polar coordinates, though. There's an ambivalence in how they're defined. So notice that in polar coordinates, if let's say this is a point with polar coordinates r and theta, so this angle is theta, what about the point whose coordinates are r, theta plus 2 pi? Well, you just added 2 pi. It brought you 360 degrees around back to the same location. So here we have two different coordinates that describe the same point. So that is a problem. It's an annoyance. We're going to have to deal with that by restricting the domain of our polar coordinate transformation. For example, if we consider T of r theta equals r cos theta, r sine theta on 0, 1 cross 0, 2 pi open. If you remember it was closed before, that would be one way of dealing with this double counting issue. So you'll have practice with that on the homework. In fact, so that now I want to talk about section 1.4, which will take what we're talking about polar and do the 3D versions of polar and cylindrical coordinates. Sorry, of polar coordinates, which are the 3D versions of polar coordinates, which are cylindrical and spherical coordinates. So being able to use cylindrical and spherical coordinates, you should be very happy about because they can save you a lot of trouble sometimes. Remember that example? Oh, okay, I'm going to flip back for a second. Let's go back to, no, not here. Back to, oh, this one right here. This was from day 3, a week ago. Now, I did this example, and I stopped short of performing the integration because look at this integral that I got stuck with. It looks rather unpleasant. In particular, it's got an integral of root x squared plus y squared, which, like, how do you even do that? Sorry? Yes, okay, good. Right. So a trig sub would be the way to do that. Let me talk about trig sub for a second. If you had to like integrate the square root of x squared plus y squared, trig sub would be the way to do it. What would be another way to do it, let's say if you ran into that on a homework problem? Yeah? Okay, yes, well, that's what we're working up to. Yeah, okay. Any other ways? You can also look at the table. You know, yeah, I mean, our textbook actually, in the front and the back, it has a table of just these kinds of integrals because this isn't 20B, right? This isn't really what we're learning here. Yeah, Kenton? I will make an announcement with regards to what you will have on the midterm. So yeah, in due time. So there's even a homework problem which has some pretty heavy trig substitution. I don't know if you guys have worked 5.4 number 15. Who's the dude that came to my office about this one? What's his name? Steven? Yeah, where's Steven at? Is that you? Yeah, right, yeah. Dude, this problem was kind of intense, right? All right, because you have to do trig substitution multiple times to do it. If you guys want to learn about trig substitution, you can look at your old calculus textbook. You can also go on my YouTube channel. Well, I posted a bunch of lectures from back when I taught 20B. I was young and dumb back then. Like, I didn't really know much about being a professor. I don't know. Like, it was one of my earlier times, so it was a bit maybe less polished. You can decide for yourself. Anyway, if you go find it, there is a trig substitution lecture there if you want to watch it to refresh your memory on that. So I thought I'd point that out. So there's also ways around this, though. If we a way better way to do this problem is using cylindrical. So look at the other slide for a second. The formula for the height of that cone was, where was it? This guy right here. In polar coordinates, this is 1 minus r. It's a lot simpler of a formula. So polar will save you a lot of trouble sometimes. Now let's do the 3D generalization of polar coordinates. By the way, you might sometimes hear the word curvilinear. That's another word for like cylindrical and spherical and other coordinate systems. So here's cylindrical. What are cylindrical coordinates? Cylindrical coordinates are given in terms of r, theta, and z of some point x, y, z are, well, they're defined as follows. They're defined by x is our cos theta, y is our sine theta, and z is just the same as it was. Z doesn't change. So let's draw a picture. Like this should look familiar because the formula looks a lot like polar. So let's say we're at some point, I don't know, let's say like right here. So this is the point x, y, z. And say this is the x and y and z axis. Okay. To find the cylindrical coordinates, I'm going to drop a line to the xy plane perpendicularly. Looks like it might go right about there. Oh, crap. Shoot. Touched the edge of my surface and accidentally... Okay, here we go. And now let's... Damn it. Draw that line. And so this is supposed to be a right angle. So this point right here would be like x, y, 0. And x, y, 0 is in the xy plane. So we can do the same polar coordinate decomposition to find that, oh, okay, well then if we label, say, this angle to be theta, let's label this angle to be theta. In that case, this side will be the radius times the sine of theta. The radius this side is apparently the square root of x squared plus y squared. This component, which is the x component, is r cosine of that angle. And the y component is r times the sine of that angle. And the z component just stays what it was, right? So z is just z. Any questions about cylindrical? You can also see the book's explanation of this if you look over here. I just copied it from the textbook, but they have their own picture. You can decide whose picture is more colorful. Aw, you're nice. Thank you. Okay, so, oops. Do a quick example with, I think we'll do spherical next. Yeah, spherical next time. Here's an example with polar. Let's find the point 223 in cylindrical coordinates. And 223 would be the x, y, and z coordinates. So I'm saying, let's say the x, y, and z coordinates are 2, 2, 3. So that would put us about right there. Okay? So what are the polar coordinates? Well, if I drop this here, this right here is theta. Can anyone read off what theta is? Pi over 4, good, 45 degrees. R is this distance right here. So that's the square root of 2 squared plus 2 squared, which is 2 root 2. And, well, z is just z. Z is what it is, which is 3, right? This is z, which is 3. So the coordinates r theta z are 2 root 2 pi over 4, 3. You should read the textbook for more examples, such as like computing the angle in other quadrants. Like I said, there's an issue of using the tan inverse function if like xy is in quadrants 2 or 3. And my number one advice for converting between polar and rectangular, always draw a picture, please. Yeah, Alex? Yes, good point. Yeah. We, by convention, yeah. Thank you.